We've already begun our discussion of sets. What we're going to talk about now are the complements of sets. And if you remember what we've already talked about, complements are things that are associated with something that are the opposite of what we're talking about. So complements in probability would be the event that's not happening as opposed to the event that is happening. We're also going to talk about subsets, and then the next video is going to be about Venn diagrams. So this is section 2.2 on complements, subsets, and Venn diagrams. Hang on, let me plug in my computer. All right, don't want to run out of power. So here we go. The universal set. Universal. If you think about universal, universe means all of it. So the universal set is going to be the set of all things being considered. So if I'm talking about the universal set of, say, phone numbers, there are pieces that are in there and pieces that aren't. So if I'm thinking about phone numbers, something that would not be in the universal set is 2/3. Now, my cell phone number would be in the universal set of all phone numbers. The school's phone number would be in the set of all the universal set of all phone numbers, but 2/3 would not be. Neither would 4.5. So that's what the universal set is. It's the set of all things that are being considered at the time. It is denoted by U. Universal set. So U is the universal set. The complement of a set is the complement, for example. So this is an example. The complement of set A is A prime. So the complement of set A is A prime. It contains, so A prime is all of the elements in the universal set that are not in A. So it's everything else that's being considered. Let's do an example to see how this works. If I'm thinking about, let the universal set, so U is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Set S is 2, 4, 6, 7. And T is X, such that X is less than 10. And X is an element of the odd counting numbers. If you would like to, you can list out the elements of T like this. So T equals the odd counting numbers less than 10. That would be 1, 3, 5, 7, 9. So those are the counting numbers, odd counting numbers, less than 10. If we want to find S prime, we simply have to look at S and U. So here's how this works. Because S prime is everything in the universal set that's in S, we're going to cross out everything in S and in the universal set. And when I go through and I cross out 2, 4, 6, and 7, everything left is S prime. So 1, 3, 5, 8, 9, and 10 would be in S prime. If I look at T prime, it's going to be everything in the universal set that's not in T. So I'm just going to cross out everything that is in T and is also in the universal set. If this is what is in T, 1, 3, 5, 7, 9, I'll cross all those out and put everything that is left. that would be 2, 4, 6, and 8. And 10. 2, 4, 6, 8, and 10. That's how this works. These are the universal set combined with examples of complements of a set. Here's an example for you to do. You can try it on your own. We can talk about it in class. So go ahead and pause here if you feel like you need to do an example, and we'll talk about it in class. Let's talk about the complement of the universal set. The complement of the universal set is equal to the empty set. If you think about it, if we're talking about everything, what is an element of everything that's not in everything? Nothing. And also, the complement of the empty set is the universal set. Because if there's nothing in the set, then everything in the universal set that's not in the empty set would be everything. It makes sense if you think about it. You might have to think about it and pause for a minute. Let's talk about subsets. For example, A, E, I, O, U is a subset of the English alphabet. Now, it has a different name. We could call it vowels, but a subset is a distinct group of a larger set. Here's how we define it in math. A is a subset of B if and only if every element of A is a member of B. And how we write that would be A is a subset of B. So if I pick something in A, it has to be in B. Not necessarily everything in B is in A, but everything in A has to be in B. Special relationships that exist. A is a subset of A for every set. Every set is a subset of itself. Also, the empty set is a subset of A for every set. And A, and if I put a slash through it, means A is not a subset of B. So those are just special relationships that exist. Let's go on. We're going to write true or false, because when we talk about sets, either something is in a set or it's not. And the way that we determine this is we take a look at what it means. So if I'm looking at this and I'm adding in these symbols because the computer would not allow me to put these in, and I'm going to give you let's see, 1, 2, 3, okay, an opportunity to evaluate the true and false nature of these. Let's look at the first one. Is 5, 10, 15, 20 a subset of 0, 5, 10, 15, 20, 25, 30? True. All elements in first set are in the second set. So that's how that goes. Are the whole numbers a subset of the natural numbers? This would be false. Whole numbers contain 0. Natural numbers does not. So 0 is in the whole numbers, but it's not in the natural numbers. What about 2, 4, 6, a subset of 2, 4, 6? What do you think? Yeah, it's true, because every set is a subset of itself. What about the empty set being a subset of 1, 2, 3? Absolutely, it's true. The empty set is a subset of every set. What about 1, 3, 5 as a subset of 1, 5, 9? Is every element in here? In here? Let's look. 1, 1, 5, 5, 3, no 3. So that's false. Is the subset an element of the universal set? Is it a subset of the universal set? True. The empty set is an element of every set. That's how this works. Okay? And so when we're doing these things, it's important to consider what we have in the set to determine what subsets are in that set. Try this example. We'll talk about it when you get to class. Thanks for watching, guys. We'll see you next time.